Hi viewers, welcome to my class on mechanics of materials. In today's class, I will work out some more numerical examples on columns. Let us start with the first example. A 2-meter long pin-ended column of square cross-section is to be made of wood. Assuming E is equal to 12 gigapascal, determine the size of the column to support a load of 95 kilonewton. Use a factor of safety 3 and Euler's crippling formula for buckling. Given that L is equal to 2 meter or 2000 mm, Young's modulus is 12 gigapascal or 12 into 10 raised to 3 Newton per mm square. The column has both ends hinged. Factor of safety is 3 and safe load is 95 kilonewton and cross section of the column is square. And we need to find out the size of this square cross section to support this safe load 95 kilonewton with a factor of safety of 3. Now let us work out. Effective length of the column L is 2000 mm. Effective length is length of the column itself. This length is 2 meter or 2000 mm. Because the ends are hinged, you can take the length of the column itself as effective length. Buckling load is safe load into factor of safety. The safe load is given as 95 kilonewton. You cannot design the column to buckle at 95 kilonewton because 95 kilonewton is a safe load you want to apply on the column. We usually get safe load as buckling load divided by factor of safety. So buckling load has to be safe load into factor of safety, or buckling load should be 3 times higher than this safe load, or 95 into 3 or 285 kilonewton, or it is 285 into 10 raised to 3 Newton. So only at 285 kilonewton the column start buckling, but we are applying only 95 kilonewton to be safe, 3 times less. So we have to design the column for a buckling load of 285 kilonewton. Euler's formula is pi square EI by L square. We know the buckling load 285 into 10 raised to 3 Newton. E value is given 12 into 10 raised to 3 Newton per mm square. I we need to calculate because column cross section is not known. So the effective length is 2000. So substituting that, you get I as 9.626 into 10 raised to 6 mm to the power of 4. So this is the moment of inertia of the column cross section, and we know that cross section is square, and let us take that A as the dimension. So A by A is the column cross section. Now the moment of inertia of this cross section is, for a rectangular cross section we calculate the moment of inertia as bh cube by 12. So in this case it is base is A, height is also A. So bh cube by 12 is A into A cube by 12 or A raised to 4 by 12. That will be the moment of inertia of the column cross section. So I is 9.626 into 10 raised to 6 mm to the power of 4. Moment of inertia of the square cross section we will get as A raised to 4 by 12. Okay. A raised to 4 by 12 is 9.626 into 10 raised to 6, or A will get as 103.67 mm. Or that is the size of the cross section required to support this load. So the square cross section should have a minimum size of 103.67 mm by 103.67 mm to support this safe load 95 kilonewton on this column. So this is a minimum size. You can have a size greater than this, but it should not go below this. So if you reduce the size, the safe load will decrease. The column cannot support so much of load. Let us work out another example. A box type column 200 mm by 100 mm, external dimensions and 25 mm thick metal is 7.6 meter long. One end of the column is fixed in position and direction, whereas the other end is fixed in position only. Find the safe load that column can carry by taking a factor of safety 3. Given E is equal to 185 giganewton per meter square and yield stress of the material 500 Newton per mm square. So length of the column is given 7.6 meter or 7600 mm. Young's modulus of the material is 185 giganewton per meter square or 185 into 10 raised to 3 Newton per mm square. And it is given that one end of the column is fixed in position and direction. That means fixed end. One end is fixed, whereas the other end is fixed in position only. That means hinged. So one end is fixed and other end is hinged. So column has one end fixed and other end hinged. Factor of safety is 3 and column cross section is a box type column with breadth 200 mm and height 100 mm and the thickness of the metal 25 mm. So the column is box type with the 200 mm by 100 mm overall size with the thickness 25 mm. These are the external dimensions of the column and thickness is 25 mm. Now let us work out effective length of the column. You can find out as L by root 2 because the one end is fixed and other end is hinged. You have to calculate the effective length as L by root 2 and length is 7.6 meter or 7600 mm divided by root 2. You will get 5374.012 mm. So this is effective length of the column. Now the external dimensions are given 200 mm by 100 mm and thickness of metal 25 mm. So this wall thickness is 25 mm. So you can calculate the internal dimensions. So 200 minus either side you should reduce 25, which will give internal dimension as 200 minus 2 times 25, which will give 150. And this height is 100 minus 2 times 25, which will give 50. So internal dimension is 150 by 50. So for a box type column, moment of inertia you can calculate as 200 into 100 cube by 12 minus internal dimension is 150 into 50 cube by 12. Okay, 200 into 100 cube by 12 minus 150 into 50 cube by 12. This 150 and 50 are internal dimensions. So this is the least moment of inertia of the column cross section. This is with respect to centroidal x-axis. Moment of inertia with respect to centroidal x-axis. If you take centroidal y-axis, you have to calculate the moment of inertia as hb cube by 12 minus again hb cube by 12. So you have to interchange this h and b. Okay, h and b if you interchange, you will get with respect to y-axis. So that will be more because this dimension you are taking cube. So 200 is more. So whichever direction you have least dimension, perpendicular centroidal axis, you should take moment of inertia. You can also calculate with respect to centroidal y-axis and find out the moment of inertia. So that will be 100 into 200 cube by 12 minus 50 into 150 cube by 12. That you can calculate and see that will be more than the value given by moment of inertia with respect to centroidal x-axis. So this is the least moment of inertia of the column cross section and it will give 15.1042 into 10 raised to 6 mm to the power of 4. So this is the least moment of inertia of the column cross section. Now in the problem anywhere they are not stated it is a long column. So we have to check whether it is a long column or short column. The given column we should check whether it is a long or short column and to apply Euler's formula. So Euler's formula before applying you should know that either it's a long or short column. In the earlier examples they have clearly given that it's a long column. So let us find out the radius of gyration. To find out the radius of gyration, we will find out the area first. area of cross section, and this is colored area, that is the area of cross section of the column. 200 into 100 minus 150 into 50. Okay, BH minus BH. So external, that overall size minus this internal dimension you should subtract. That will give the area of this colored portion. So 200 into 100 minus 150 into 50, or 12,500 mm square. So that is the area of cross section of the column. Now radius of gyration you can find out as root of I by A. I you have calculated the least moment of inertia, and this is going to be least radius of gyration. So K is root of I by A. I is 15.1042 into 10 raised to 6, which we have calculated, divided by area is 12,500, which will work out as 34.761. So this is the least radius of gyration, and the column in this case can buckle only in this direction, because with respect to this axis you have least moment of inertia, and the column buckling chance is only in this direction. It cannot buckle in this direction, okay, because it will offer more resistance to buckling in this direction. So column can only buckle in this direction, that is which axis you have least moment of inertia, in the perpendicular direction it can buckle. So you got the least radius of gyration. Now you can find out the slenderness ratio. You can find out the slenderness ratio of the given column. L by K, effective length divided by least radius of gyration. That will give the slenderness ratio. We have effective length calculated earlier divided by least radius of gyration, which will give the slenderness ratio of the given column as 154.6. This is the slenderness ratio of the given column. Now critical value of slenderness ratio you should calculate based on the material property. So material property, you know the Young's modulus and yield stress of the material. So critical value of L by K is given by root of pi square E by sigma C. Pi square into Young's modulus is given 185 into 10 raised to 3, and sigma C also, that is yield stress of the material, is given, so 500. That is the load at which the column fails. Due to the direct stress induced, the column fails at this stress 500 Newton. The material starts yielding, so that is a failure point. So 500 is the yield stress, sigma C is 500. You can substitute that and you can get the critical value of slenderness ratio for this material as 60.43. So for the given material, the critical value of slenderness ratio is 60.43, and our column made out of this material has a slenderness ratio 154.6. So this is greater than the critical value of slenderness ratio. So the given column is a long column and Euler's formula is applicable. It is a long column and Euler's formula is valid. So you can apply Euler's formula. Okay. So Euler's buckling load is given by pi square EI by L square. Pi square into Young's modulus is 185 into 10 raised to 3. I we calculated 15.1042 into 10 raised to 6, and L effective length you can substitute. Okay, so you get 954,930.88 Newton or 954.93 kilonewton. So this is the buckling load given by Euler's formula. So column will fail due to buckling at this load. If you calculate the crushing load, you can calculate as sigma CA. Sigma C, that is yield stress into area of cross section. If you calculate, that is will give the crushing load. This is a buckling. This will give a less load compared to the crushing load given by sigma CA. You can calculate sigma C and check, and that has to be greater than this, because we have checked the validity of Euler's formula. So column will fail due to buckling than due to crushing. So it has to fail at a load less than the crushing load given by sigma CA. So we got the buckling load using Euler's formula. We also know that factor of safety as 3. So buckling load divided by factor of safety. This is the load at which the column buckles. So to be safe, you have to apply load less than this and by a factor 3, because the application requires a factor of safety of 3. So you want to reduce the load on the column. We cannot load up to buckling, so we are reducing that by a factor 3. So dividing the buckling load by 3, you will get the safe load as 318.31 kilonewton. So this is a safe load the column can support. And that's all for today. Thank you for watching.